What's up? Oh, it's only when I have my sound on do you hear that. It's the same. All right. So, this is CSC300. It picks up where 250 left off last semester. So we'll actually just continue on with that same slide set. Just keep going. Most of you know me. Here's my cell phone number, 262-353-6205. Best way to reach me is either text or email. You can call if you want, but I won't answer. I only answer the phone from my wife, and she knows that it has to be an emergency. This is when the class meets, blah, blah, blah. Here's the textbook that you're supposed to have from when you were in 150 or something. I won't use it. Blah, blah, blah. Okay, grades. 40% of your grades, homework assignments, 20% quizzes, 20% midterm, 20% final. As usual, if you bomb the midterm and then you do well in the final, I'll replace your midterm grade with whatever you got in the final, but not the other way around. So you don't get to do well in the midterm and then blow off the final and expect me to double the midterm grade. Quizzes are meant to make sure you're paying attention in class, so I typically give quizzes at the very beginning of a class. They're meant to be fairly easy. If you've been following along in class and paying attention and doing your homework on your own and that kind of stuff, your quiz grade should easily be above a 90%. So if it's not, that means that you're sucking in multiple ways. Well, at least one way, but potentially multiple ways. So suck less. Grading scale, normal 90, 80, 70, 60, blah, blah, blah. Questions, comments, concerns, bribes. All right, so that's the syllabus. There is also a textbook for you to purchase. It's $450, payable to me. It's actually online. You can get it for free. It's just linked on the website. This is legally usable, so it's not we're not cheating anything. Data Structures and Algorithm Analysis is the name of the book. I will give you some reading assignments out of this, and we will maybe do some exercises out of this, but this covers some of the stuff we'll be dealing with in class in here. All right, so most of you who've had my classes before know I typically don't use a textbook. Sometimes I do use them, like in this situation, but I rarely make you buy them. I just think spending $200 or $300 on a book is kind of ridiculous. Okay. Especially when you have books that you can't sell back. You're stuck with this like $250 calc book that's like meaningless to you. It's dumb. Okay. Questions about any of that crap? All right. So let's pick up kind of where we left off at the end of last semester. We had started talking about objects, and we're going to continue that on this semester. This semester, we're going to be talking about something called data structures. And I'll introduce those here in a few minutes. But just to review quickly, what does this keyword do? I have it up on the screen. You can read it. Okay. This, when we're writing our own objects, creating our own objects, this is how an object refers to itself from within itself. Okay, so if you are inside the code for an object and you need to talk about yourself, you say this dot. I want to call one of my instance variables. I want to call one of my instance methods this dot. Super keyword is how an object refers to its parent. Okay, remember that in object-oriented languages, we have a top-level object that exists in the language already. That is the object called, in Java, it's object. In C#, it's object with a lowercase o. In Objective-C, it's NS object. In Visual Basic, it's probably something made up like ice cream cone or something like that. So, in any case, this is part of the structure of object-oriented languages, what makes them work. If you take the 470 class with me, which is programming language theory, where we write our own programming language, when we write an object-oriented language, part of it is we need to create the existence of a top-level object to support all other objects. Okay? So this guy already exists in Java. So when we write our own objects, like last semester we wrote this fraction class, this guy is a object. So it's part of this hierarchy here. So if we are inside of an instance of the fraction class, the this keyword is how fraction refers to himself. Super is how fraction refers to the instance of his parent. Okay? So in this case, fraction would be a superset of the object type. So when we create an instance of a new fraction, let me just show you that real quick. When I say fraction f is equal to new fraction, and I think we took like a numerator and denominator in as parameter, so that would be the fraction 1/2, something like that. When we do that, behind the scenes, this is what's happening. Inside this fraction class, we get a variable called this, which is equal to draw my picture, which is equal to the same thing f is equal to. These are pointers. Okay, and I'll show you that here in a second. Similarly, inside of that fraction class, we get a variable created for us called super. Now, unbeknownst to us, when we created that fraction, something else was created as well. So we didn't actually do this, but an instance of the object class was created. And then it was superseded. It was, we put some stuff on the outside to turn this guy into a fraction. So this was kind of our starting point for this object, and then we made him into a specialized object called a fraction. And super, in this case, points to that O, same place. So that's your parent in this particular case. Okay? Now, if we change this model up a little bit, and we say we have an object and a fraction, and then a dumb fraction. So just another class, where dumb fraction inherits from fraction, which inherits from object. So now we have 3 levels here. So if that was the case, when we created a dumb fraction, dumb fraction df is equal to a new dumb fraction. And let's say dumb fractions don't take in any parameters. Instead, they just generically create the dumb fraction 1/1, which is just 1, which is a kind of a worthless fraction. So what's happening here is when we create df, it's creating an instance of f, which is also creating an instance of o. Well, an instance of object and an instance of fraction. So 3 different instances get created here. Okay? And at the low level, at the dumb fraction level, within that class, within that instance, we get this, which points to df. And then we also get a variable called super, which points to dumb fraction's parent. In this particular case, because the hierarchy looks like this, dumb fraction's parent is fraction, whose parent is object. Does that make sense? So in this particular case, super would point to the same place that f points to. So if we are inside the dumb fraction class, and dumb fraction needs to access something that belongs to fraction, it would reference that using super keyword. Inside the fraction class, we would have a super variable which would point to the instance of object which was above them. So this is like a family tree. Does that make sense? All right. Kind of reminded me, any of you have been watching that, I'm not sure why I don't hate it, but it's surprisingly funny. Just on TV, Actually, the season just ended, called Gallivant. You know what I'm talking about? It's like a singing comedy thing. There was a funny thing in the other day. There was like one of the royal families saying, you know, they wanted her to marry the cousin or something like that. Our family tree goes straight up, no branches, no branches. And I thought that was funny. Okay, so this is how objects are organized, and that's what the this and the super keyword do. All right. So before we go any farther, let's kind of review that stuff. So I'm going to go ahead, I'm going to create a new project here in Eclipse for CSC300 Spring 2015. Good enough. And we'll go ahead and create our new class driver. Surely you all remember how to write the Hello World program, right? Oh, help me. Don't just trust us. So if I had given that as a quiz today, we would all gotten it right? That's good. I'm not sure I believe you. But if that's true, I would have been impressed. Okay, so just real quickly, I always create my initial object. I tend to call it driver just because it connects it to other parts of computer science. When we think about software drivers for our graphics cards or something like that, what is that? It's the piece of software that makes your program run, makes your hardware run, something like that. So this is our core program that makes everything else we write run. So I call it driver, but you can call it whatever you want. All right, and I always start with a nice little hello world or something just to make sure everything's linking right. So hit play, we get our hello world. So far so good, Eclipse works. Okay, so good way to start off. Typically, if you think that something's broken with Eclipse, it's not Eclipse, it's you. But every now and then it could be Eclipse. I have seen Eclipse do weird things before because obviously I never make mistakes. Right? All right. So what we're going to do here, just to kind of see our little example from our hierarchy there, I'm going to create a couple of objects. So we're going to go ahead and we're going to create a new class. We'll call this guy dumb fraction. Okay. And the dumb fraction is going to keep track of no, actually before, I'm not going to fill in dumb fraction yet. I'm also going to create another new class called fraction. And we're not going to make our fractions do a lot at this point. Well, probably not at any point since we wrote them some last semester, but whatever. So fraction is going to keep track of a, now we did talk about public, private, protected last semester, right? Is that a or a uh-huh? No? Okay, fine. See, that's why I have to continue on with the slide set, because every time I teach 300, it picks up at a different point, depending on where we got on 250. All right, so we're going to create an int numerator, an int denominator, and then we're going to have a constructor for fractions that's going to take an int numerator and an int denominator. And I want to go ahead and set my numerator equal to numerator and my denominator equal to denominator. So I just say this, right? Numerator is equal to numerator. Denominator is equal to, I usually have trouble with denominator. Fingers move funny. I did all right that time. All right, so what's wrong with this? I want to set my numerator from up here equal to the numerator that was passed into this constructor, right? That's why I'd like to happen. What's actually happening right here? Well, something's happening. Effectively nothing. It's setting that version of numerator equal to itself. Probably not what we want, right? So effectively, this does nothing. So the crappy way of fixing this would be name these guys different. Don't name this numerator, name it num, so that you can refer to numerator as being the guy up there and num as being the guy right here. Well, that's kind of a dumb way of doing it because we want our variable names to be expressive. When somebody creates a fraction and they go and look at your documentation or they look at your fraction class here and they see, oh, here's the constructor. How do we know that's a constructor? Same name as the class. Constructors always match the name of the class. Okay? Case sensitive and all. So we know this guy's the constructor because its name is fraction, the class name is fraction. And so we're going to look at that constructor. We're going to say, okay, this tells us how do we build one of these guys. Okay? And then we're going to look at the numerator and denominator. These are the parameters. Parameters that go into building a fraction. So when I go out to driver and I want to create a fraction object, I'm going to say fraction f is equal to new fraction. I know so far that this is the correct way of writing it because if I want to create one of these, I call a constructor with the same name. Now I jump into the fraction class and I need to look at what is required in here for me to build a fraction. What does the constructor need for it to work? So I go to my fraction class, I look at the constructor. Some classes might have multiple constructors. What's it called when you have more than one thing with the same name but a different number and or type of parameters? Polymorphism. All right, so I look and see, oh, this guy takes two parameters. Now, if I called this parameter x and y, and you were just looking at this, do you really know what x and y are? Is that very descriptive? Does it give you a whole lot of information about what kind? I mean, I know I'm supposed to pass in two integers, but what do they represent? Maybe you can look at this and say, well, I'm building fractions, so these probably represent the numerator and denominator, but is x the numerator and y is the denominator, or is it the other way around? See what I'm saying? This isn't real descriptive. Well, you can always add a comment. X is the numerator. Y is the denominator. Something like that. And maybe clear it up at least a little bit. But wouldn't you agree that this is a lot more descriptive? We probably want to name our variable names appropriately rather than change the name of them so that we don't have to understand this part. Make sense? All right, so that means we need to know how to fix this. We really want to set that version of numerator equal to this version of numerator. Now you mentioned to me that what I'm doing right here is I'm setting this guy equal to himself. Why is that? Explain why that line does that. Definitely involves scope. Tell me more.
Because it's only that variable is created within that instance of that function.
Okay, so generically speaking, when I look at that variable, a variable resolves to what? What does this variable resolve to? It resolves to this guy right here, right? You can actually tell because when I highlight it, this guy shows up in yellow. But it resolves to its most local definition. We have two definitions of numerator here. We have we have this definition of numerator, and we have this definition of numerator. Two separate guys, same name, but in different scopes, as he pointed out. All right. So when I use a variable name, it has to get resolved at runtime. And a variable will always resolve to its most local definition. So numerator right here will resolve to its most local definition. So what we're going to do is we're going to look at the local environment first. That is the environment created as part of this method, this constructor. Okay, so we have two different environments that are created in this case right here. Let me kind of show this. Tell you what, when in the 470 class, when we write variable environments, oh, that's a blast. You guys will just be crying. So good. So, variable environments. In this particular case, we have our fraction class. So inside of our fraction class here, we have two variables created. Then we have our fraction constructor. And the fraction constructor has two variables created. All right? So inside of this, let's see how do I want to do this. I really like drawing pictures. It's so much fun. It's like a 4-year-old. All right. Oh, yeah. Oh, I got to fill it. I want the text to be a new color. Is it under text?
Yeah, there's a little color swatch. It's underneath 20-point font.
Oh, haha. All right, there. So we really have, and let me copy this real quick. And I want to send this guy to the back. And actually, let's make this guy just a little bit different color. All right. So, in our current example, this is kind of what we're dealing with. We have this fraction class that has its own environment. So this gray thing is the environment generated by the fraction class. And inside of that environment, we have two different things that exist. We have, well, three different things. We have an int numerator, an int denominator, so two variable definitions. And then we also have the definition of a method, a constructor in this case. Okay? So these three things are at the same level. They all live within the scope of the environment created with the fraction class. Now, when the fraction constructor was written, its own more local scope, a subscope, if you will, was generated. That's part of just the fraction constructor. Okay? And inside of that scope, we define two variables. Make sense? Now we have a couple of lines of code that we wrote. So these are some lines of code that exist within this, this environment. So these are variables defined locally in that environment, and here's some lines of code that happen within that environment. Now, a variable always resolves to its most local definition. So when I say numerator here, or I say numerator here, the very first thing we're going to do is we are going to check the variables that were defined in that environment. And we find that numerator is there. So both of these guys resolve to this version of numerator rather than this guy there. That make sense? Now, this is our topmost environment. in this particular case. This is our topmost environment. And this is the environment that belongs to the fraction class. Every fraction that we create gets its own top-level environment. So if I created a fraction f, a fraction f1, a fraction f2, a fraction f3, each of those fractions will have their own copy of this environment with their own copy of numerator and denominator. Make sense? And those fractions, as we talked about a few minutes ago, when they're created, a variable called this is magically created. So actually, up here, we have an additional, I'll just call it pointer, an additional variable that's of type pointer called this. We also have a variable of type pointer called super. So these are all variables that were created. We wrote 2 of them. The other 2 were automatically created for us as part of Java's magic that happens behind the scenes. Okay? So this is what's going down at this top level environment. And I just mentioned we maybe created 4 fractions. So f has its own copy of numerator, denominator, this, and super. So this would point to the same place that f lives in memory. f1, own copy of numerator, denominator, and its own copy of this, which points to where f1 lives in memory. f2, f3 as well. Okay, so there's 4 different versions of this variable in that particular case, one owned by each instance or each copy of the created fraction class. Okay, so we know that we can access the fraction class itself, this particular instance of the fraction class, through the this keyword. Now, when we say numerator equals numerator down here, a variable always resolves to its most local definition, and we see that the most local definition is defined inside of this environment. The one I've defined is white, this white environment, a sub-environment within the more global environment. Now, what we actually want to say here is we want to say that variable numerator, the one up here, is equal to the one right here. And we do that by specifying that this dot numerator is equal to numerator. So that version of numerator right there will resolve to its most local definition right here. This version of numerator, because we prefaced it with this dot, we've given it the full path of where it lives. So we've said, by the way, don't try to resolve this in the normal way. I've told you where you can find it. You can find it in this guy's top level environment. Does that make sense? So this gray environment I've drawn here is owned by this particular instance of fraction. And I've told it you can find the variable I'm interested in here at the top level environment by saying this dot. So we circumvent it even looking locally. Similarly, we can say this dot there. That make sense? Really important concept, the this keyword. I know I said that last semester as well, but it's very important that we understand what's being created here. This isn't difficult, but it's still something we need to reconcile in our mind. When to use this and when not to use this. Okay? Now, if I had changed these guys to num and denom, is this still legal? You say yes. Tell me why.
It's still inside the fraction construction. Still inside the...
Well, yeah, nothing changed there, but what does this line mean? Remember, all variables resolve to their most local definition. So what does num resolve to? This guy right here? The most local definition of num? What about this guy? Does he resolve to its most local definition? Officially, yes, but does it actually try to resolve like that? Or does it just go where it is? Does this dot says go to the top level environment? And it finds numerator there. Legal? Yeah. Is there a numerator at the top level environment? Is there a num at the local environment here? Or is there a num somewhere? You know, it's here. We'll find it locally. But if it wasn't here and it was here, we'd still be fine. It would find it, right? So this is perfectly legal. Is that legal? I mean, I've only changed it for numerator, not denominator. Does that break it? It'll resolve. This does a little bit extra work. Because what it'll do is that since I didn't tell it specifically where to go look for it, it'll look for numerator in this local environment. And when it doesn't find it, it won't give up yet. It'll say, oh, I do have another environment that I can jump to and see if I find it there. So after it looks here, it will look to the next environment up. It happens to find it there, and we're good to go. But if I had said Bob here, it's going to look locally, not find Bob, jump up to the next environment, not find Bob, and then realize that was the top level environment. I've exhausted my options. And that's when it gives you the red underline that says there's a problem. Variable cannot be resolved to a definition. Make sense? So the punchline here is we don't want to be forced to change our local variable names to make it so that we don't have to use the this keyword. We should be comfortable with the this keyword. It's not difficult to use as long as we can paint this picture in our mind of how an object is organized. Okay? All right, questions about any of that? Let's continue to explore here. I think I need to, there we go. Let's go back to Eclipse. So here's my fraction, numerator, denominator, and we're going to say public. I'm going to give myself another method here. Void display, and this guy's going to do a system.out.println this. Okay, so I just created a method called display, which effectively does what? Gives us another method in here. I'm just trying to stick with my we have the display method. Display method gets its own environment associated with it that's inside the more global environment, but we haven't defined any variables there, right? So right now that display method has one line of code in there. And is that line of code legal? What kind of animal is that? Cat, dog, object, method, variable. Those are your options. It's variable. And all variables resolve to what? Most local definition. So what are we going to do? We're going to look locally here first. Because when I go to print this out, it's going to have to resolve this variable before it can print. It needs to know what that variable is, right? So we're going to look locally in our local environment. I just highlighted there. Does it find a definition of this there? Doesn't find any variables there. So are we out of luck? Just throw an error? Nope, we're going to go up to the next local environment. What's the next most local environment to this guy? The gray environment there, the parent class, well, the top level class, not this guy. These two environments are independent environments that live within the more global environment. That makes sense? So if I'm in this environment right here and I can't find the variable I'm looking for here, I don't get to check here. Those guys aren't linked. You can't, there's no road that goes there. The only road that leaves here is the road to here. Okay, and its variable environment is defined right up there. Do I find this defined somewhere up there? Right here. And what kind of animal is this? It's a variable of type what? Pointer. What's a pointer? It's a primitive type capable of holding a memory address. So when I print this out here, what should print? Memory address. All right, good enough. So we'll print out our memory address. We'll update these lines of code up here to support what we've written in our slide. All right, so there's our fraction class. And let's go into driver real quick. And we'll go ahead and just create a fraction, even though we don't use the 1 and 2 at all. Just that supports our syntax. The constructor for fraction requires that we pass it 2 integers. So I will pass it my 2 integers, it will store those 2 integers, and we never use them again. Okay, so we only have one ability here, and that's called display. So now I'll call my display method. Now remind me, class method or instance method? What was that? Tell me why he's wrong. No static keyword. So class methods are defined using the keyword static in front of the method. Instance methods don't have static. So since there's no static in front of this, it's an instance method. How do we call instance methods? Using an instance of the class in which the method was defined. What class was this method defined in? Fraction. Do I have an instance of the fraction class out here? It's stored within the variable named f. So I'll say f dot display. Okay, what should print out to the screen? Memory address. Now remember, where's my previous page? There we go. Remember what I showed here. Right now we're in the model where dumb fraction doesn't exist yet. So we'll just drag that down there. So this points to F, super points to O. Okay, so we just printed off, oh, wrong arrows. I was tricking you and you all missed it. Good enough. So the this keyword, this variable, points to the memory address associated with F. So if I say system.out.println F, all variables resolve to their most local definition, right? What's the most local definition of F? This guy right here. There's 2 environments created here. Here's your local environment, and then you have your more global environment. So on our other slide, this is the white environment, and this is our gray environment. Okay? So when I go to print out F, in order to print it out, it must resolve that variable. F is going to resolve to its most local definition. Its most local definition is this variable right here. And what kind of value does F hold? Memory address. How do you know? New keyword. New keywords our real estate agent goes and gets us a memory address, right? So we know F holds a memory address. And this slide says that this inside of this particular instance of fraction points to the same place that F points to. Because it's how an object refers to itself within itself. When I'm in the fraction class and I say this, I'm referring to myself. This particular instance of fraction, I'm saying set my version of numerator equal to the variable you passed in. Set my version of denominator equal to the variable that was passed in. Display my address where I live in memory. That make sense? What's the output of this program going to be right now? I create a fraction. I call that fraction's display method, which displays the value stored in this. And then I print out F. What's the output of this program going to be?
Same memory address twice.
Same memory address twice. Very important. So we see that inside of the fraction class, when we use the keyword this, it resolved to the same memory address as F resolved to outside of the fraction class. Which then proves to us that the this keyword is how an object refers to itself within itself, because inside the fraction class, we don't have the variable F. F was a local variable in main. So F is a variable that holds the pointer to this particular fraction, the one fraction I've created here. So we have access to F inside of this local environment right here. So I can refer to this fraction over and over and over again inside of this local environment by using the variable F. But if I'm inside the fraction class, I don't have access to that variable F from out here. It was local to this environment. But sometimes, and we've seen already an example of that sometime, an object needs to refer to itself. So built into an object-oriented language is typically the automatic creation of a variable of type pointer that points to this instance of the variable. So in our example here, this and F are synonyms. They both hold the same value. Inside of fraction, we have to say this because we don't have access to any other way of holding our memory address. Make sense? In driver, we have F. So we do have a way of accessing. That particular fraction. Does that mean I should be able to say this out here and it still work? I'm currently in the process of tricking you, just so you all keep remembering that. Clearly it doesn't work because we get a red underline, right? But I'm not going to show you why you got that red underline. Why doesn't this work here? Go ahead.
Outside the fraction class.
Okay, outside the fraction class. Well,
Is it because main's the highest?
Let's run with what he said first. The real answer actually isn't either of those. But the path I want to take you down involves kind of what he's saying. Okay, so we're outside of the fraction class. As far as we can tell, we don't have a variable called this here, right? Let's go write a dumb fraction. So we're actually, before I write dumb fraction, I want to go into the fraction class, and I want to add a little invisible line here that's already there, but I'm going to spray the, for the invisible ink. How does the invisible ink show up? How do you make it show up? Is it light? Time? Oh, yeah, that's right. I learned that from, what's the name of that? Yeah, National Treasure. They put lemon juice on the Declaration of Independence. I think I also saw it on one of those Finding Bigfoot shows. They put lemon juice on one of Bigfoot's hairs or something. I don't know. Turned out to be human hair. And the scientist was like, oh, he was relieved because all Bigfoot hair comes back as human. I would have been more concerned if it would have come back as like a North American brown bear or something. I don't know. The guy didn't seem credible to me. I happen to think there might be something like a Bigfoot type thing, like a, some big apey type thing. But this guy he seemed off to me. So the show, Unearthing America is the name of the show. I think that's what it is. Yeah, that guy seems like a scam artist. I am watching the season finale right now. He's doing the Da Vinci Code type stuff. Like talking about bloodline of Jesus and that kind of stuff, which I find fascinating. I don't know if there's truth to it or not, but I don't know. Seems more romantic to me than that there's some cup or something from the Last Supper. I don't know. Whatever. Made a good movie and a book. All right, so we're going to go in and we're going to create, I was putting the invisible ink thing here, that's right. So right here is something called extends object. We didn't see it, but I promise you it was there. Okay, still not complaining about it. It's perfectly happy with us hard coding it in there, but it was there even without us hard coding it. And what that did is it says fraction is one of these at its core. What I wrote there supports this slide. Our top level was not fraction. Our top level is the object class that's built into Java. Because all objects have to come by this guy. This is a very, very, very important object that doesn't do much other than support the structure of how objects, generic objects, must work in the Java environment. Make sense? So this guy exists. We rarely will use features of the object class. It has some methods in there and stuff like that, and sometimes it might be handy. We'll look at it in more detail as this course goes on, but generally speaking, we only care about objects so long as far as they support the creation of our own objects. Make sense? All right, so we have our fraction, and fraction extends object. It inherits from object. It is one of these guys. Okay, so we wrote that. Now we're going to go into dumb fraction, and up here we're going to say extends fraction. Okay, a dumb fraction extends fraction. Is that like an NFL highlight thing?
Well, no, it was a wrestling thing with a mixture of WWE.
So this is what the students are doing these days during class.
Well, I didn't mean to click on it.
You meant to click on the Beyonce video. My phone's blowing up. Well, something's blowing up. Oh, it's like an outside. All right. So, fraction, or dumb fraction extends fraction, which supports this connection. Make sense? So we've created a little hierarchy here. We have a dumb fraction, which is a fraction, which is an object.
So what doesn't it like?
We haven't written the constructor yet. It's fine. Nothing's broken yet. We just haven't done anything. All right. So now we're going to go ahead and we're going to write the constructor for dumb fraction. And we decided dumb fractions take in no parameters. And what we're going to do to create a dumb fraction, we'll do this a couple different ways. I'm going to say numerator is equal to 1, denominator is equal to 1. I'm not going to do that yet. Pretend like this isn't a red underline. Steel. Okay, so forgetting that this is a red underline for a different reason that we'll fix in a second. I just wanted to show you this first. When we create a dumb fraction, we're actually creating the fraction 1 over 1. That's our intent. Okay? Now, is this legal code? Notice that these aren't underlined in red. Okay? So is this legal code? Can you tell me why, for any other reason other than they're not underlined in red? Okay, so variables always resolve to their most local definition, right? Well, so I have a variable here called numerator. Here's this local environment. Is there a numerator defined there? Nope. So we jump to our next most local environment. Is there a numerator defined there? Not yet. Close. We're not there yet. No, we don't see one, right? We see no variables defined right there. But instead of being done like we were before, and really we weren't done before either. When we were back here, after we didn't find something here, remember when we had Bob? It would have checked the local environment associated with object. And we could probably just assume the generic object written in Java probably doesn't have a variable called Bob. Okay, so we kind of ended it there, but there is that more global environment there that we didn't draw. So that is in this slide. There would be one at the very top level associated with object. Okay, that all objects get as the default. So back here in dumb fraction, we don't find numerator in this environment. We don't find numerator in this environment. So what do? We jump up to our next environment to check, which is the one that we inherited from fraction. And in there, so that's this environment right here. Not the ones that are encompassed inside those. These are our white environments in here. We don't have access there. So it's the global environment of fractions at the top level here. He has another class he's got to get to. He's not just being rude. I hate this class. All right, so we do find numerator here. So before we ran out of places to check, we did find a local definition of numerator. Okay, go ahead.
If we were to use the super keyword and dumb fraction, would it refer off to fraction?
Yep. So we can say that. Super.numerator, super.denominator. That's keeping us from checking here and just telling us to go directly to here. Make sense? So that's how super would work. So that supports our connection. How an instance of a class refers to its parent from within itself. The instance of its parent. Remember when I drew this one, when we created our fraction object, behind the scenes, an instance of object was created. Just like in this case, when we created our dumb fraction object, behind the scenes, an instance of fraction was created, as well as an instance of object. So 3 separate instances are created from us actually writing the code to create one variable instance of dumb fraction because of the inheritance model. Dumb fraction extends fraction, so that means we need to create a fraction object to support that inheritance. And fraction, by default, extends object, so that means we need to create an instance of object to support that inheritance model. Make sense? So we could say super dot here as well.
So do we have to tell dumb fraction that it extends fraction?
Right here.
but we have to do that.
Yes.
In order for the
Oh, yeah,
object
yeah.
to work.
If we don't put anything up there, it's assumed to extend object.
Object, yeah.
Yeah, because that's why the object-oriented language works. That's just part of there must be a beginning type thing. But yeah, so if we don't put anything up here, it's assumed to be extends object. In fact, you would very, very rarely, if ever, in Java see anybody write that. It's one of the reasons that I like to show some examples in Objective-C. I've said this in the previous class too. I'm a big fan of the Objective-C programming language from a teaching perspective because it doesn't hide so much from you. It forces you to extend object. You have to say in Objective-C, it's :ns object, or :ns object like that. So it forces you to extend it. It's not it doesn't do automatic stuff for you very often. It also forces you to instantiate this in super if you want them. So it's the things that I'm showing you today exist in Java that are being done for us, like the creation of those variables in a language, older languages like C++ and Objective-C from the same vintage, let's say, force you to do it, which I think is instructive to see it. So that's why I'm kind of putting some stuff in here that isn't required so we can actually see it. Okay, so let's go back into dumb fraction. So super dot refers to the same place, but keeps us from having to look in so many spots. Just takes us right to our parent. Let's just jump there. Make sense? All right. Now, the thing it's complaining about here is built into the inheritance model in Java is the ability to call your parent's constructor. And it must happen on the very first line. Okay, the very first line of your constructor. So what we're going to do here is we're going to say super (1,1). The idea here is if dumb fraction is in fact a fraction, it very likely could be partially created in terms of its parent, right? So, we could have a Boolean is useless variable here, and we could say this dot is useless is equal to true. That's what makes dumb fractions special. Okay, that's what makes them different than just a fraction. But generally speaking, a dumb fraction is defined in terms of its parent. So what we're going to do is we're going to go ahead and utilize our parent's constructor. So this is saying super here is a synonym for saying fraction. But we can't say fraction here. It doesn't support because constructors always follow the new keyword. Remember that?
Did you do that though? Or no?
We can't because what we're setting up here is this. And we don't have access to create the this keyword. So we have a special construct in Java that allows us to directly call our parent's constructor through the super keyword. Make sense? But the special rule here is if you're going to call your parent's constructor like this, it has to happen on the first line. Has to happen on the first line. So remember, our parent's constructor takes in two parameters, a numerator and denominator. So I'm going to go ahead and pass it 1 and 1. Numerator of 1, denominator of 1. So it'll call that fraction constructor, set up the numerator and denominator for this guy, which dumb fraction inherits because it extends fraction. And then we have a more local variable here in dumb fraction called is useless. And we'll set that to true. That's what makes dumb fractions a little bit different than fractions. So dumb fractions require you to not pass a numerator and denominator because it just passes in, it just creates a fraction with a 1 over 1. Okay, creates the fraction 1. And then it sets this local variable called is useless to true for no good reason otherwise other than just to show us the structure here. Okay, so that's a dumb fraction. Go back into driver. Dumb fraction the constructor takes in, no parameters, because it hard codes in the inputs to the parent's constructor. So we don't pass in any parameters out here. So now we created a dumb fraction. What abilities does dumb fraction have? Can I say system.out.println df? This is inside main. Is df a variable that's in scope? Yep. What kind of value does df hold? Memory address. So what's going to print out right here? Memory address. So 3 things print out here. We're going to call f, which is our instance of fraction, his display method, which prints out this. Then we're going to print out f. And as we had before, these 2 lines should print out the same memory address. One of them happens internally, one happens externally. But we see that they're connected. This is how an instance refers to itself from within itself. What memory address is this guy going to print out? A different one, right? At the very least, not the same memory address as the previous 2. All right? So 2 identical memory addresses, and then the new address associated with dumb fraction. Can I say df.display? But if you go into dumb fraction, we didn't write a display method. So not just variables resolve to the most local definition. Methods resolve to the most local definition. So when I come to driver and I say df.display, it's going to initially look, now the way I'm calling this is display an instance method or a class method based on how you're seeing me call it. Instance method, how do you know? Calling it with an instance of the class instead of the class name. So this must be an instance method. So the first thing it's going to do is it's going to dive into df, dumb fraction, and it's going to look for display to be somewhere in here. That make sense? Does it see one? No. But we're not out of environments yet. So it jumps up to the next level, fraction. Does it see a display method in here? It does. So it's going to call this method, which prints out this. Make sense? All right. Remember, I was going to trick you. We've seen that these 2 lines print out the same memory address. We saw that this line printed out a new memory address. What will this print out? Same as this one? But isn't dumb fraction doesn't have a display method. Fraction has a display method, which has its own variable called this.
But it's still taking the same memory address. Or same numbers.
Same memory address, right? Printed out the same memory address twice. This is an important caveat. Important thing here. Like I've illustrated here, when we created a dumb fraction, a fraction was also created. An object was also created, right? 3 different variable instances were created. Each one of those variable instances got its own this and super, which was created. So in this model right here, we actually have 3 different thises and supers. I assume object creates a super Probably just equals null or something like that, but doesn't matter. We really only care about these two levels here. So dumb fraction has a this, which points to this instance of dumb fraction, and dumb fraction has a super, which points to this instance of fraction. Fraction has a this, which points to this instance of fraction, and fraction has a super, which points to an instance of object. Object has a this, which points to itself, that instance of object, and has a super, which points nowhere, because there's nothing above object. Make sense? Now, we follow the yellow brick road here. In driver, when I say df.display, and it comes into dumb fraction, and it sees that there is not a display method here, it jumps up to the next level and sees that, oh, there is a display method here. And this display method is inside of the fraction class, and it's displaying this. But out here, when we saw it run, which version of this did it display? The one associated with dumb fraction. Why is that?
Because when it creates a new one every single time, it's associated with that one class, right? Instance.
Well, it has to do with variable resolution. A variable always resolves to its most local definition. So if when I print out system.out.println this right here from a dumb fraction, and this resolves to its most local definition, and we're seeing that it's resolving to a definition of dumb fraction, that means it's resolving to dumb fractions version of this, not fractions version of this. What does that tell us about how the inheritance model works? When I called the display method, did it actually go up to the fraction class to find display? Or did display make itself available to dumb fraction? This dot display. If I'm in dumb fraction and I say this, that refers to this particular instance of dumb fraction, correct? And if I say this dot and it gives me display as an option, that means that display was brought into dumb fraction as a component that it owns. We don't actually have to search for it above. We got our own copy. That makes sense? Similarly, and we saw this happen before, I was able to put this dot numerator in this dot denominator right here, right? Remember when I had that? That means that dumb fraction isn't relying on the fraction above to get to numerator and denominator. It brings those in when it was born. Okay? So it inherited some traits from its parent, and those became local traits of dumb fractions. It was born with those abilities. Make sense? They were copied from the parent, but they're housed within the local. So just like people, right? Okay? So those become local things. So a question I have then, in dumb fraction, if I have a display method, and I think I need to make it public, because did I make it public in fraction? I did. Don't worry about the public stuff right now, we'll talk about it. So in dumb fraction, if I write a display method that says blah, we come out here, what's going to display right there? The most local definition of the display method. There's our blah. But wait a minute. Didn't we just discuss that dumb fraction automatically gets its own copy of all those methods? Its own copy of all those instance variables?
Is it only
Effectively, yes. What we did here is we did something called override the method. We chose, rather than to inherit the display method from our parent, we chose to write our own. That make sense? Chose to write our own, which circumvented the inheritance model for this one part. Okay, gene therapy, if you will. We were born in terms of our parent. We got everything the parent gave to us. But wait a minute. Gene therapy upgrade. At runtime, we inserted our own display method rather than take the one that was handed to us by the parent. Make sense? But we can still utilize the parent's display method. It's still there. We didn't kill it. We just suppressed it. That makes sense? So I can still access it by using the super keyword. So now, dumb fractions display method does two things. It prints out blah, then it calls upon its parent display method. And its parent display method prints out a memory address. Look at the memory address it prints out. Still prints out the memory address of dumb fraction. If I go into fraction, and after I print out this, I say system.out.println super. It does not let me get at the memory address of my parent. The parent here is object. Well, can I print out super in dumb fraction? I can't. Over here, I've advertised that this and super are the same kind of animal. They're both pointers. One is a protected pointer. The other one is an open pointer. Super we cannot access by memory. And part of that is how Java works in terms of virtual machines. Java has its own memory model. So it hides the details of how it supports this hierarchy of objects from us. So we can't go and walk memory with Java. Protected memory system. This gives us access to ourselves, and it appears to us that throughout the inheritance model here, if we started in dumb fraction, and dumb fraction was the dude who called the parent's display method, the this here resolves to dumb fractions version of this, not fractions version of this. Okay, so this is regardless of whether we overrode a method or not. This refers to the starting point, the instance of the starting point. Does that make sense? Okay, so we'll stop there. We'll come back on Thursday. We'll kind of finish up this review. We've gone into a little bit more detail than we went into last semester. And then we'll start talking about data structures. I'll see everybody then. Could be a quiz. Could be a quiz on Thursday. No promises.
Lunch.
Yeah.